Hi everyone, I'm Tongjian and I'm here to present our paper, Deep Learning-Based Webshell Detection Coping with Long Text and Lexical Ambiguity. Webshell is a piece of web scripting language program written for providing remote access and code execution to server functions. Hackers may use webshells to do one or more of the following harmful tasks, such as stealing information, tampering databases, modifying the home page of a website, uploading malware, intruding other machines in internal network, and escalating hackers' privileges to cause more serious damages. In addition to the severe consequences caused by Webshell, a research of Microsoft detection and response team announced a steady increasing number of these attacks too. The Webshell detection methods can be classified to three main categories by features they are using and by how the features are generated. They are traditional methods, machine learning method, and deep learning method. Traditional detection methods are used based on string signature matching algorithm and some statistical information of web shells like number of function calls, information atrophy. Although traditional methods can efficiently detect existing web shell, they are also subject to lack of generalization ability, fail to detect an unseen web shell, of which the signatures or patterns are not in the databases. And then machine learning detection methods can automatically discover the relationships between features and Webshell, benign PHPs by learning from large and varied data. Although machine learning methods perform better than traditional methods, they have the disadvantage of using handcrafted features which need to be delicately designed by specialists, and of like PHP code semantic awareness because they commonly use statistically engineered features to train a model. Deep learning detection methods have been proposed to mitigate defections of machine learning methods. Deep learning algorithms such as convolution neural network and long short-term memory have the abilities of extracting features automatically from numerous data. Although these proposed deep learning methods show a promising prospect in Webshell detection tasks, they are subject to challenges of coping with long text and lexical ambiguity. Besides, in model training procedures, there is also a challenge of decline of model generalization ability if samples are not treated reasonably. In the scope of natural language processing, it is challenging when deep learning models process long text input. Long input leads to an expensive model computation and memory space cost. This is because the higher complexity in nowadays models such as LSTM, Transformer, and BERT. Take self-attention module in Transformer for example. The computation and space complexity are both O, L squared, where L is the length of input. And long text challenge also exists in Webshell detection task. We collected over 100,000 PHP samples from GitHub high-ranking projects and our production systems, finding that the median of token count of benign and Webshell samples are 1,000 and 3,000 respectively. In formal research, some text selection methods have been utilized, such as token filter and length fixed text truncation. However, token filter methods cut the whole text into inconsecutive fragments, so downstream deep learning model can hardly be exploited for further mining code semantic because neighboring context is not sufficiently preserved. And the text truncation method preserve a part of consecutive text and throw away the remainder, so they face the problems of overlooking important information and holding reluctant information when coming to long PHP text. To deal with long text, a more semantically friendly text selection method is necessary in Webshell detection task. In text analysis perspective, token filter methods belongs to a micro-lexical level granularity which might ignore the semantic in neighboring contexts, whereas text truncation method belongs to macro-document level granularity which might lose the focus of a high-value information of the text. Such a medium sentence level granularity text selection method should be researched for both preserving consecutive context and removing reluctant information from long PHP text. And in the scope of NLP, lexical ambiguity is the potential for multiple interpretations of a word or phrase. Lexical ambiguity implies it's difficult or impossible to understand the word meaning without some additional contextual information. This challenge also exists in unnatural languages such as programming languages. For instance, two status tokens exist in the following PHP code fragments. The first status token in curl status represents a key or a field member, while the second status token in status equals to false represents a local variable which has a totally different code semantic meaning with the first status token. Besides, there might exist multiple status reference and multiple status assignments in this PHP script. For a more concise semantically comprehension, different representation vectors of this status token should be generated by token embedding methods. However, commonly used embedding methods such as word vector or one-hot encoding method generated identical vector for identical token, such fail to deal with lexical ambiguity. Lexical ambiguity in NLP scope can be addressed by BERT-like model architectures. These architectures are mainly based on transformer encoder which contains a series of self-attention models. Besides, BERT-like models have also been successfully exploited in cybersecurity scope, including malware detection, cybersecurity name identity recognition, reverse engineering. So, in Webshell detection tasks, the possibility of resolving lexical ambiguity by BERT-like model should be studied. Besides these two challenges in terms of data processing and model architecture, challenges also exist in model generalization aspect. Meaning data sets used in many Webshell detection literature are often consist of benign samples downloaded from GitHub public projects. After a deprecation process, all benign samples are mixed together with Webshell samples into a whole dataset, from which training and validation datasets are randomly chosen. However, this seemingly reasonable sample speed process will cause data leakage to an extent in the validation dataset of a benign sample. As a consequence, model with relative lower generalization ability will be selected in training procedure. The main reason lies in that benign PHP scripts in the same GitHub project may have a bunch of project-specific code expressions, such as same class names, same function names, and the same programming styles. And the randomly chosen data split method will split a part of one benign project in training dataset, and the other part of the exactly same project in validation dataset. This randomly split method may cause a high similarity between training and validation dataset. Take these four PHP scripts in Figure 1, for instance. Scripting A and B both belongs to a high-ranking GitHub PHP project, and script C and D to another high-ranking GitHub PHP project. It is shown that project-specific class names and code styles to do exist between A and B, which is the same situation between C and D. In randomly data splitting method, if A and C are chosen to training dataset, while B and D to validation dataset, Then while the performance on this validation decide what will be selected is a Webshell detection model that identifies some project-specific text content as important features, such as class name, base command in both A and B, and use dispatchable expression in both C and D. In other words, instead of mining complex semantic features from code logic, a model that easily remembers these semantically irrelevant and project-specific features will perform well in validation side and thus be selected as a suitable model to detect those unseen PHPs. This obviously will cause a somewhat decline of generalization ability, so it is necessary to amend the size split method to a moderate level of randomness. The selected model should mine code semantically in depth and learn from non-project specific information. To mitigate these challenges in Webshell detection task, we present a new method with following contributions. Contribution 1. Propose a TextRank-based sentence-level text selection model that preserves relatively consecutive code, semantic, and filter out reluctant information. Contribution 2. Propose a more concise code token vector representation model using CodeBert framework by taking lexical ambiguity into consideration. And contribution 3. Use a training validation data size split method with randomness in project granularity to address data leakage problem and promote model generalization ability. Besides these three contributions, we use an actual large benign PHP dataset to adequately validate false positive rate. False positive rate is a more crucial performance indicator, even comparing with false negative rate in practical applications, since Webshell alarms need further checked and handled by human labor in intrusion detection systems. Higher FPREs, higher labor cost system needs, and this dataset is the largest among Webshell detection literature to the best of our knowledge. The overview of our method architecture is shown on the slide. It is a two-stage deep learning method consists of three submodels: a text selection model, a token embedding model, and a downstream classifier model. Model functions and inputs/outputs are briefly listed. Text selection model aims at extracting high-value information from source code and cutting off reluctant information on sentence-level granularity. The input text selection model is PHP script. The output is crucial semantic information, which in our case is a number of complete code lines. Token embedding model receives code tokens of the selected code lines as important and output vector representations of every single token, and also an overall vector representation of the whole selected lines. For identical code token in various code contexts, different vector representations are generated by taking lexical ambiguity into consideration. To capture semantic information in a more extensive way, as usual way of NLP training, we adopt an embedding model which is already pre-trained in advance with task-relevant code. Then we fine-tune this model with task-relevant Webshell and benign PHPs. Then a token vectors are fed to a downstream classifier to further mine code semantic. Many of models can be used as classifier, including deep learning and machine learning models. These classifiers output the probability of a PHP script belongs to the Webshell. Model loss is calculated and utilized to train the classifier and to fine-tune the embedded model. In our method, TextRank model is adopted to extract high-value text from PHP script. TextRank, a variation of PageRank, is a weighted graph-based model proposed for automatically extraction-based summarization. TextRank produces a graph nodes ranking without the needs of labeled data. Ranking score calculation is mainly according to the similarity between nodes as formula below. Nodes with higher ranking score represent better summarization of text. In our implementation, graph nodes of TextRank are PHP code lines which are separated by end-of-line character. The similarity between a node pair is calculated by token co-occurrence similarity mentioned in literature 28. Then the ranking score of each code line is calculated by iterations as formula shown on this slide. Important code lines are selected in a descending order of ranking score, starting with the highest score and ending when the count of selected tokens has achieved a threshold, which in our work is 512, or when reaching the end of PHP script. Since TextRank is an unsupervised algorithm, the classifying loss of stage 2 will not be back propagated to the text selection model in stage 1. It means that the parameter of this TextRank remain identical in training and inference phase. And to cope with lexical ambiguity challenge, in token embedding procedure, we adopt CodeBert, which is essentially a BERT framework pre-trained language model proposed in programming language scope. Pre-training language model is trained in advance by a large amount of data via a self-supervised way and is later fine-tuned by a moderated amount of data in downstream tasks. As a BERT counterpart in programming language scope, CodeBert is also based on stacked transformer encoder and is pre-trained with the codes of 6 programming languages including PHP, Java, Python. CodeBert differs from BERT in that the model is training with unimodal data and binomial data including pairs of programming language and natural language. In our work, we use official open-source pre-training model parameters of CodeBert as initial parameters of a token embedding model. Then the parameters are fine-tuned by collective Webshell benign PHP scripts in training phase. We tokenize output code lines of text selection model into code tokens, which are further fed into CodeBert to generate token vector representations. Among multiple layers of CodeBert, we use output vector of last transformers layer as representations of code tokens. Representations vector of whole selected code lines is noted by output vector in CLS location, since the CLS vector contains synthetic semantic information of PHP script. It can be directly used to detect Webshell by combining with light machine learning classifiers such as softmax. However, downstream deep learning classifier can also be exploited on token vectors to mine more semantic information. For further mining code semantics, we use TextCNN model as a downstream Webshell benign classifier. TextCNN has been utilized in cybersecurity scope, such as code analysis and vulnerability detection. CNN is a neural network that includes convolutional computation originally applied to the imaging domain. It was transformed by research in literature 31 to TextCNN for text field application. TextCNN performs corresponding convolution and pooling operations on the input text vector using various sizes of sliding windows to capture both local features and global features. Note that convolution kernels has length in 2 dimensions, one of which always aligns with the dimension of code token representation vector, while the other is the kernel size. So a slide of convolution kernel on input is more like an n-gram feature extraction method, which n is equal with the kernel size. Max pooling operations are taken on the feature maps, which are outputted by the convolution layer. Then a concat layer gathers all features in one hidden vector. Finally, a fully connected layer transforms this hidden vector to output vector. The length of the output vector is equal to 2, which means 2 classes. After this all model implementation, a more detailed architecture of our Webshell detection method is shown on this slide. And in our experiment, after the duplication process, about 21,000 benign samples are collected from 38 GitHub PHP projects, while 5,000 Webshell samples are collected from both GitHub and our production systems. These benign and Webshell samples are noted as dataset D. We first randomly chosen 12 benign projects and 544 Webshells from D to form an evaluation dataset. Then, for the split of training validation dataset from the rest of D, noted as D star, we use two types of data split for showing the existence of data leakage. Split type 1 randomly shuffle samples in D star, then cut 80% of D star for training and 20% remainder for validation. Split type 2 for benign project randomly shuffle in project granularities and cut 80% of benign projects for training and then 20% remainder projects for validation. While for the Webshell sample, the split data set remains the same with split type 1. For more clearance, green color part is for training date on this page. Green color part is for validation date, while orange part is for evaluation date. Note that evaluation date is identical for both split type 1 and type 2. And we train 3 models using both split type 1 and split type 2 for the demonstration of data leakage in validation dataset and the model generalization ability affected by this data leakage. In this experiment, ChargeBoost based model with n-gram feature engineering, softmax based model with word vector feature engineering, and our method are training used both data split type 1 and split type 2. The model with best performance on validation dataset are selected for result comparisons on evaluation dataset for all 3 detection methods. It can be seen from table 1 on this slide that method trained by data split type 2 both perform better than split type 1 on evaluation dataset, which is unseen in training phase. Though the recall of word vector with softmax in split type 1 slightly surpasses split type 2, the precision decreases largely. This means the decline of generalization ability actually exists when model is trained by GitHub benign projects, while data split type 1, which based on randomly shuffle in script granularity. Split type 2 with project granularity shuffle should be used for avoiding the data leakage in validation site and for enhancing the ability of generalization to unseen PHPs. So in other experiments, we will adopt only data split type 2 to drop split type 1. In experiment 2, we introduced 3 similar deep learning-based Webshell detection method, which also contain a text selection model, a token embedding model, and a downstream classifier. Besides, 3 frequently used Webshell detect software are also detected. FPR indicators of these 6 approaches and our method are further evaluation on almost 86,000 benign PHPs. The results are shown in this table on this slide. Note that the Webshell killer software has 2 detection modes to choose. One mode is for higher recall and the other mode is for higher precision. It can be seen that our method surpasses all detection approaches in recall and F1 score, while Webshell killer software in mode 2 achieves the highest precision, however, at the expense of the lowest recall. Since these detection software are commonly based on signatures and rule-based models, they achieve an average higher precision and lower recall than the set of deep learning-based models. Comparing with other deep learning models, our method performs better on all 4 indicators. The lower FPR means that our method needs a lower manual labor in disposing of the false alarm in practical application, with a percentage of 33%, 10%, and 40% of deep learning method 1, 2, and 3, respectively. Our evaluation dataset also contains 117 of Webshells. And as a conclusion in this work, a two-stage model for Webshell detection is proposed to mitigate the challenge of coping with long text in deep learning detection method and the challenge of programming language lexical ambiguity. A TextRank-based sentence-level text selection method is utilized to extract high-value information from PHPs, and the CodeBert-based token embedding method is utilized to generalize token vectors. TextCNN is used as a downstream classifier to detect Webshell and to fine-tune the embedding model. We prove the existence of data leakage of training if benign data is collected from GitHub project, but not reasonably split. To avoid the decline of generalization ability caused by this data leakage, we propose a more reasonable data split method with shuffle samples in project granularity. We collect 26,000 PHP samples to train and evaluate our method. Besides, an extra-large benign set is also used to test the false positive indicator, which is a crucial concern in practical application. Evaluation results show our method improved the performance of Webshell detection. And thank you for your listening.